Hi guys, hello and welcome to today's session. And in this session, I am going to cover a basic primer on IP addressing. And we are specifically talking about IP version 4 and not version 6. I'll be covering IP version 6 in my next video. Now, to get started, I will be assuming that you do not have any prior experience on IP addressing, and we are going to start right at the basics. So, it is really a complex subject, so I am only going to go as far and as deep as you need to know in order to get started with basic IP addressing in general. And by end of this particular video, you would be comfortable with concepts like IP addresses, subnet mask, concept of supernetting, subnetting, class and classless IP addresses, concept of CIDR blocks. So basically, all of this will help you get started with Amazon VPCs and IP address allocations and creating your subnets. So the concept of IP addressing wouldn't be alien to you. Now, there will be some areas of the subject where you may want to go deeper, and there are a lot of resources out on the internet for doing that. So, let's get started with the very first topic. Okay, to kick off this session, let's start with an IP address. Now, let's say we have a web server on the internet and you want to communicate with that web server. Now, the web server is likely to have some kind of a network interface, and attached to that network interface will be an IP address. And this is going to be a public IP address. In this case, because the web server is available via the internet, IP addresses are the addresses that the computer would use to communicate to this web server. So essentially, this IP would be a public IP. So you have got your computer at home and you have a web browser open and you type in example.com. Now, what happens is that as soon as you type in example.com, your computer needs to contact a nearest DNS server to fetch the corresponding IP address of the web server where this request is to be routed to. So your computer would send in a request, a query to fetch the IP address corresponding to example.com. The DNS server basically is a lookup database of domain names where you can find the corresponding IP addresses. So once the query is received, the DNS server would look up in its database for example.com and it will return the corresponding IP address of example.com back to the computer. The computer, as soon as it receives this IP address, it would redirect the request to the IP address, and that's the IP address for our web server. Once our web server receives the request, it is going to respond back to that request with the relevant requested data by the user. And once that response is received by the computer, it would load and display the relevant fetched information on the web page. And this is what is called the domain name resolution, wherein the human readable, easily rememberable address of your web server is resolving to an IP address, which is a much more difficult to remember format. So basically here the IP address is being mapped with a domain name, but essentially they both are the addresses to your web server to fetch the information from your web server. So even though example.com is being used in the front end, in the back end, essentially what establishes the communication between the two computers for exchange of information is the IP address. So that is what an IP address is essentially um, important for. So whether it is the wide area network or the local area network, IP addressing is the key to the information exchange that happens between computers. Let's move on to the structure of an IP address. Now you have seen IP address in our previous slide that was attached to our web server. So an IP address might look like 192.168.0.1. Now this IP address as a whole is 32 bits of information. Now this is segmented into four parts, and this representation is called dotted decimal notation. And each of these segments that you see separated by the dots are called the octets. And each octet is 8 bits of information. So 8 bits of 4 segments of information, or 4 octets of information, that is a total of 32 bit of information. So a total of 32 bits make these 4 octets here. So this is where things get a little bit more complex. So what is a binary octet? An octet means that you have 8 values, and those values can either be zeros or ones. Please note that when I'm talking about these 8 values, these are 8 binary values. So in this table here, you can see that the very first row here is all ones. So it is 8 bit of information which is representing one octet. So each octet is a representation of 8 bits of information. So here what you see in the first row is the binary values, and what you see in the row below is the corresponding decimal values. Now on the left hand side, we have what is called the most significant bit. That means that if we have a 1 in the leftmost place, it's going to have a decimal value of 128. Now, if you have a 1 on the right hand side, that is the least significant bit, and its value is going to be only 1. If you have a 0 anywhere, like as an example of the third octet, all the corresponding decimal values are 0, so all the binary equivalents would be 0. And if you have a 1 anywhere, as in case of the last octet, you can see that for the least significant bit, we have a 1 in a decimal place, so the corresponding binary value is 1. But for the remaining 7 bits, the decimal values are 0, so the corresponding binary values are 0, and hence this is the binary representation of the last octet. Similarly, for the very first octet, the decimal value is 192, which is a combination or the summation of 128 and 64, which is the most significant bit and then the bit after. So these two bits are non-zero. The decimal values are non-zero, so the corresponding binary values are 1. But for the remaining bits, the decimal values are 0, hence the binary values corresponding to them will be zeros. Hence the binary representation would be like this. Now coming on to the second octet, which is 168. It is summation of 128, which is the first bit, and then the third bit, which is 32, and then 8, which is the fifth bit. But the remaining bits are not are the decimal corresponding decimal values are 0. Hence the binary values would also be 0, and this is how what will be the binary representation of the second octet. So the reason it is important to understand this binary is when we get to subnetting with variable length subnet mask, which will be covering in the later part of the video. So what you need to remember here is that a IP address is a total of 32 bit of information, and it has 4 octets, and each octet is 8 bit of an information, and the max decimal value representation of each octet is a summation of the corresponding decimal values of each bit in within the octet, and which is going to be 255 and not more than that. So basically, when each of these octets are always going to be max 255 in its decimal value representation and not beyond that. And how this is calculated is by summation of the corresponding decimal values of each of these 8 bits of information. So that's all for this section. Let's move on to the next slide. So firstly, let's understand network and host portion of IP address. So every IP address has a network ID and a host ID. The first three octet represented by the green boxes on the left here represent the network ID. This value will be same for every computer in this network. The host ID represented by the last octet in the orange box here will be unique for every computer on this network. As I said before, every IP address will have a network and a host ID, but how this is configured does vary. Now, how do we know which piece of the IP address is network ID and which is the host ID? And that is where subnet mask comes into play. Now we have 255 in the very first octet. Essentially, there we will have 8 bit, that is a 1, and that represents the network ID. As you can remember from previous slide, the table here represents the 8 bit in the octet where all 8 bits are 1. Summing up the decimal values gives us 255. So here we have 8 bits that are 1 in the very first octet, 8 bits that are 1 in the second octet, and 8 bits that are 1 in third octet. So those first 3 octets are representing the network ID. Now the last octet in the orange box here is going to be the host ID. That's why it is 0. So every bit in the subnet mask that is a 0 means that's where we have values that can be assigned to a host. And every octet that's a 1, those are values that are going to be exactly same for every computer on the network, representing the network IDs. So a subnet mask is an easy way to see which octet of an IP address represents the network IDs and which octet contains the host IDs. So let's check this out with an example here. We have a network 192.168.0.0 with a subnet mask that looks like this. Now this is a 24-bit subnet mask because we have 8 ones in those first 3 octets, and that means that it is a /24 network. It is another way of representing a subnet mask. Now, how 24 bits is because each of this octet you know that is 8-bit long, and since 3 of the octets are dedicated towards the network, you have 8 plus 8 plus 8, that is like 24 bits dedicated towards the network. So on this network we might have several computers, and Each of them may have different host IDs. So in this case, the host IDs are 1, 2, 3, 4, 5, and 6. Whereas you can see that the first three octets they remain constant, hence representing the network portion of the ID. So moving on, for all the hosts on the network, we also have something called classes with IP address. A 32-bit IP address is divided into 5 subclasses: a class A, class B, class C, class D, and class E. So for class A, B, and C, what you see in green here is representative of the bits allocated towards the network, um, towards the network. And what you see in orange here are the octets and the bits that are um, allocated towards the host part of the network. So let's move on and deep dive into each of these classes. And before we move forward, let's remember that within any IP range, the first IP and the last IP are reserved for the network number and the broadcast IP. So a class A IP address are assigned to network that contains a large number of hosts. Network ID, as evident here, is 8-bit long, and the host ID, which occupies the rest 3 octets, is 24-bit long. The most significant bit of the first octet that you see here, it's always reserved to be 0. So that leaves the remaining 7-bit in the first octet to determine the network ID. The 24-bit of host ID are used to determine the host in any network. The default subnet mask of class A is 255.x.x.x. Therefore, a class A has a total of 126 network address. Now, how this is calculated is that you raise 2 to the power 7, where 7 is the number of bits allocated towards your network addressing. And here we saw that we have only one octet towards the network addressing, and within that the first bit is reserved towards the class A addressing, and we have only 7 bits towards the network addressing. So we raise 2 to the power 7, and then we subtract 2 from this range is because the first address is used to communicate within the network. It's kind of a network number, and then the last range is a loopback address. So in terms of the number of hosts that can be added to this particular class, can be calculated by raising the number of host bits to the power of 2, and then again subtract 2 from the resultant, and that would give you the number of host addresses. And this is the range of IP addresses that is supported by class A. So a class A looks like this. Here you have an 8-bit subnet mask, and that means that the first assignable address is going to be a 1, and you can't ever assign a 0 as an address for a computer on the network. And the last assignable address is going to be 254, because you can't use 255, which is a broadcasting address. Now there are a few other addresses that are reserved with class A. And with a class A subnet mask, you can have up to 126 network, and each of those network can have a huge number of hosts, that is 16,777,214. So now coming to class B, IP address belonging to class B are assigned to a network that ranges from medium size to large size network. So the network ID as evident here is spanning 2 octet. That means it's 16-bit long. Similarly, the host ID is spanning 2 octets, so it is also 16-bit long. The most significant bit of the first octet in class B is always set to 10. So that leaves you with remaining 14 bits, that is combining these 2 octets. So you have 14 bits in the first and second octet that are used to determine a network ID. The 16 bit of the host ID are used to determine the host in any network. The default subnet mask of a class A is 255.255.x.x. Therefore, a class B has a total of 2 to the power 14, again as described in our previous section for class A. So this is representative of the number of bits that you can use for your network addressing. And because the first 2 bits are reserved, you have the remaining 14 bits for the network addressing. And so you raise 2 to the power 14, and that gives you 16,384 network addresses. Now, on the host addresses, you are going to raise 2 to the power of a number of bits for host addressing, and that is spanning 2 octets. So that is 2 into 8, 16. So, and then you are going to subtract 2 because, as explained, that 2 of your starting and ending IP addresses are reserved. So the typical range looks like this for a class B address. Now let's have a look at an example. So we got a class B which has 16-bit subnet mask. The first assignable address is 172.16.0.1 based on this example here. So, and for this example, the last address would be .254 because the 255 address is used for the for broadcasting. So here we have 16,382 networks. So a lot more network and usable addresses per network has reduced now to 65,534. So you can see that while class A had less number of networks and a huge number of host addresses, class B is a little balanced with an increased number of network but a reduced number of um, host IDs per network. Okay, so now let's have a look at class C IP address. IP address belonging to class C are assigned to small sized network. The network ID is spanning 3 octet is 24-bit long, and the host ID spanning 1 octet is 8-bit long. The most significant bit of the first octet in class C is always set to 110, and that leaves us with remaining 21 bits spanning the first, second, and third octet to be used for the network addressing. And since the host addressing is limited to 1 octet, so we have 8 bits dedicated for the host addressing. The subnet mask, as evident here, would look like 255, 255, 255, and the last octet being dedicated for the host addressing. So therefore, a C class has total of this many network, and how do we calculate it is quite evident from our previous discussions also. So we raise uh, 2 to the power of number of bits available for host addressing. So as I told you here, the first 3 bits are allocated and they are reserved for class C type of IP addresses, Hence, we are left with 21 bits here. So we raise 2 to the power 21 to get number of networks that are possible out of a C class IP address. And similarly, for the number of hosts that can be supported, we raise 2 to the power to the number of bits that is available for host addressing, which is 8 in this case. But we remove two IP addresses, which is the very first IP address that would be uh, used for the network ID, and the very last address, which is used for the uh, loopback or broadcasting. So we remove those two IP addresses from the range, and we get 254, which is the number of hosts that can be supported in Class C IP address. And again, this is a reference to the IP range that is possible in a Class C IP. Now let's have a look at an Class C example with actual IP address. So suppose if I am working with a network 192.168.0 dot and going beyond, like with this host address, the subnet mask would look like this. And the first assignable IP would be 192.168.0.1 for this network, and the last would be 4. And again, as discussed, the very first IP, which is dot 0, and the very last IP, which is dot 55, dot 255, would be reserved. Hence, we cannot use it. And the total number of network would be quite high, as you can see here, whereas the number of usable IP addresses per network would be limited to 254. So Class C IP address, in a sense, supports a large number of network, but the number of hosts that can reside within each of these network is going to be small and restricted to 254 hosts per network. Okay, so now let's have a look at what is Class D and Class E IP addresses. So Class D IP address belongs to a category of IP addresses that is used for multicasting. Now, what is a multicasting? So in general, vast majority of day-to-day traffic that we work with on IP network is of unicast variety. That is one source device sending to another destination device. But IP addresses also support multicasting, where a source device can send to a group of devices. So multicasting is not used a great deal on the internet, mainly due to lack of widespread hardware support. So most of our focus is on on unicast IP addressing. So multicast is useful in certain circumstances, however, especially as more efficient alternative to broadcasting. So that is what multicasting is, which is supported by Class D IP addresses. So a Class D IP address is the starting bits are always set to 1110, and the remaining all the bits are dedicated towards the host addressing. And that's what is Class D IP addresses. And the range for the IP address is from 224.0.0.0 to 239.255.255.255. Now, this is all about Class D IP addresses, and in addition to that, we have Class E. Now, Class E is a set of reserved IP address which are used for experimental and research purposes. The IP addresses in Class E range from 240.0.0.0 to 255, 255, 255, 254, and this class doesn't have again any subnet mask. The most significant bit of the first octet of class E is again always set to 1111, and all the remaining bits are dedicated towards the host addressing. So in a general day-to-day work, you won't be dealing too much with class D or class E set of IP addresses. Now moving on, you have these ranges of IP addresses which are private IP address that are reserved for private use according to IETF RFC 9 1981 document. So these IP addresses are never meant to be allocated to any public facing uh, servers or devices. Okay, now that we have had a look at all the classes of IP address, now given a scenario wherein you are having an IP address and you want to determine back which class this IP address is belonging to, all that you have to do is take the first octet and whatever decimal value you have, you convert to binary equivalent of that octet. And once you have derived that 8 bit of the first octet, you can just determine that by looking at the starting bits. So for example, if it is starting with a 0, you can easily determine that this IP is a class A IP. And similarly, if it starts with 10, then you can determine that it's class B and thereon. So this is the simplest way by which you can identify an IP to which class it belongs to. Now, the problems with classful IP addressing are plenty. The problem with this method is that millions of Class A addresses are wasted. Many of Class B addresses are wasted, whereas number of addresses available in Class C is so small that it cannot cater to the needs of the organization. Now, Class D addresses are used for multicasting and therefore available as a single block only, and Class E addresses are reserved and private. So, since there are these problems, classful networking was replaced by what we know as classless interdomain routing or CIDR in 1993. We'll discuss classless addressing in the next slide. Sometimes we want to vary the length of our subnet mask and we don't want to stick to those standard subnets in the classful IP addressing context that we saw earlier. And the reason to avoid those standard subnet mask is the limitation that it introduces in efficient use of IP addressing. We already saw in classful IP addressing that in some contexts like class A, IP addresses, the number of networks are low as compared to the overall number of addresses that can be allocated per network. Similarly, as in case of class C, you could see a reverse of class A, wherein the number of networks that could be allocated are quite high, but the number of addresses that could be allocated to the host are quite low and limited to 256. And this leads into inefficient use of IP space. And we, in order to avoid this, we use something that we call as classless interdomain routing, and this helps us optimize the IP space. We already discussed the challenges associated with classful IP addressing in our previous slide as well. So a CIDR network is identified with a trailing slash, as you can see here, followed by a number that indicates how many bits are used to identify the network portion of the address. So a slash 24 would indicate that 24 bits are used to identify the network and the remaining 8 bits are used to identify the host. So let's have a look at an example here, and we have a network ID 192.168.0.0. And let's say that we have this network here with a 24-bit subnet mask, and we have 8 host bits, and that leads to 254 possible unique IP addresses that can be attached to the hosts on this network. So that leads to the first allocatable IP address as 0.1 and last one as 0.254. And please note that we cannot use 255 because that IP address is the last IP address in the range and it will be used for broadcasting. And the very first IP in this range, that is 0.0, is the network ID. Hence, those are two reserved IP spaces and cannot be allocated to any host. Now let's have a look at a 16-bit subnet mask. So with the same network, that is 192.168, we are using a different subnet mask, a non-standard one in this case, because if you remember correctly, 192.168 is typically a class C network. But remember, we are now talking about classless IP addresses. So to revive the memory quickly, let's go back to an example slide that we had on class C IP address. So you can see the network ID 192.168 is the same that we use here, but the subnet mask that was standard in classful IP addressing was spanning 3 octets. Whereas if you come back to the slide here, you see that we are intending to use only 2 octets, that is 16 network bits. And this is pretty standard with context to CIDR, but non-standard when it comes to classful IP addressing. So a 16-bit subnet mask here, it would mean that 16 host bits are available, and which would lead to 65,534 unique addresses that can be allocated to a host. And the first IP in that range would be a 0.1, and the last IP address in this range would be 255.254. Now, what about a /20 subnet mask? Is that even possible? Well, in context to a classless interdomain routing, that is a pretty much achievable uh, context. Here you can see that we have used some bits from the third octet, or we have shared some bits from the third octet of the network octet with the host octet, and that leads to 12 host bits and 20 network bits as against 24. So we have borrowed 4 network bits into the host bits, and that gives us a total of 12 host bits, which leads to 4094 unique IP addresses, and the range looks something like this. So sometimes this is a better configuration for the number of computers you need to have on the network and the number of networks you actually need. And the address for this network, as you see here, starts from 0.1, ends at 15.254. So that's classless interdomain routing, or CIDR, and it is using a variable length subnet mask. So in other words, breaking away from standard and optimizing the amount of network and hosts that we can have. Now, given that you have a CIDR block or a notation, you can calculate the number of usable IP addresses from your CIDR notation. So a CIDR notation can range from /8 to /30. It could also range up to /31, but a /31 would be indicative of just one IP address in that range. So in order to calculate the number of available hosts, the formula is pretty simple. You take 32, as in like 32 bits are the bits, that maximum bit that the IP represents, and from that you are subtracting the number of network bits, because the trailing number after trailing slash in the CIDR notation is indicative of the number of bits dedicated to the network portion of the address, and you subtract that from 32, and the value that you get, you raise it to the power of 2, and what you get is the number of IP addresses that can be allocated in that range. That does not allocated, but that falls in that CIDR block. Now, in order to calculate the number of allocatable IP addresses from that range, you need to remove the first and the last IP address. Hence, you see we subtract two IP addresses from that number of hosts, and what you get now is the number of IP addresses that you can allocate to the host. So that is a pretty simple formula, and moving forward, you can also calculate the subnet mask from your CIDR notation. So the process to determine the subnet mask is pretty straightforward. So the number of bits in the network portion of the address are converted to ones and padded with 0 until you have 32 number. And then you divide the number into 4 octets, and from there it's all about converting each of your octets into decimal format. And just to refresh your memory how to calculate the decimal player values from your octet, we used the reference of this table of 8 bits which was representing each of the octet, with the first row depicting the binary values and the last row depicting the equivalent of the decimal values. So summing up the decimal values would give you the decimal um, value for the octets in your subnet mask. So that's how you calculate subnet mask. Now we will touch base on a couple of concepts here in context to CIDR, and that is subnetting and supernetting. These are important topics, and we have laid the foundation in our previous chapter for you to understand this concept. So, the subnetting is all about how many smaller networks you could fit into a CIDR, a given CIDR block. So, as this question states, how many slash 29 networks can fit into a slash 28 network? In order to understand this question better, let's move over to one of the slides we used earlier. So as from this table, you can understand that the range for a CIDR notation can start from /8 and go up till /30, wherein /A is the largest network and /30 is the smallest network. A /31 is indicative of only one IP, so that doesn't qualifies to be called a network. So we have skipped that out. But that if you see a /31, you can understand that we are talking about only one IP. So the question states that how many /29 networks can fit into /28, and you can determine the size of the network by looking at the available hosts. So you can see a /28 has a larger number of hosts as compared to /29. So if I have to calculate how many /29 networks could be accommodated in a /28, 6 multiplied by 2 is 12, multiplied by 3 is 18. So 18 wouldn't fit because we are going overboard by 4 IP addresses. So the most feasible one is 612 host addresses to be fitted into a /28. So that would mean a 2/29 network can be accommodated in a /28 network. Now, this is a crude way of calculating it, but if you want to apply a technique to calculate this, the steps that you can follow is like this. So subtract the network bits from 32 for both the networks and then raise it to the power of 2. And then once you have done that, you divide the larger network by the smaller network. And then what you get as a value is the number of networks, that number of slash 29 networks, or the smaller network that can be fit into the larger network in the equation. So to state, a slash 28 is the larger CIDR block, and you are subnetting it to two subnets that is having a slash 29 CIDR block. So each of these two CIDR blocks are the subnet of the CIDR block, and they can host 6 IP addresses each. Now, this is what is subnetting. If you reverse this concept to have smaller network to form a larger network, that is what is called subnetting. So this is a technique to calculate how many networks you could accommodate within a CIDR block. So or subnet you could accommodate within the block, but that doesn't lead to it because you would need some further information like, okay, what is the IP address range is supported within your subnets and other queries. And if you want to further break it down to have more number of subnets, how many. So for planning my subnet, I what I use is a tool, a visual subnet calculator tool that I have hosted on this URL here. I will provide the link to this URL in the description below, and you could also play around with this tool, and this will give you a fair idea on planning out your subnetting with a subnet with a CIDR block. So all that you need to do here is the mask bits you can subnet mask bits you can update. So for example, we were talking about a slash 28 network. So if I update, what it would give me are a few information that gives me a much better idea and control over my planning for the subnetting activity. So as here you can see the usable IP address range and number of hosts. And if I want to break this CIDR block further into two subnets, I can just use the divide operation, and you can see that while the top level block is a slash 28 CIDR block. The subnets that consist of slash 29 CIDR block are available here, and which means that this with this operation I'm hosting 6 um, IP addresses in each of these CIDR blocks. So we can have 2 slash 29 blocks within slash 28 block. Now I don't suppose if I don't want to have like 6 um, devices in my network, I know for sure I want to have only 2 in each subnet. If I divide this further down, I can see that I can have 4 network with 2 devices each, or 4 subnets with 2 devices each within the same subnet uh, or within the same CIDR block. So you can play around with this tool in order to deep dive into the concept of CIDR, block, subnetting, and the relevant informations that you would require will be all available via this tool. But having said that, it is to understand the basics, it's important to understand how the calculation techniques and the formulas, the reference for which has been provided to you in my uh, earlier slides. So now moving forward, even with CIDR blocks, we have some reserved IP addresses like 10.0.0 slash 8, which is reserved for private and internal use on your internet, and it could be used but not on a public facing internet. Similarly, 127.0.0/8 is a block that you use for loopback addresses or local host and stuff like that. And similarly for the rest of the IP addresses are here for, or the CIDR blocks are here for your reference. So that's all for the primer session on IP addressing. I think that you will have all the prerequisite information to get started with IP addressing in general, which would help you in understanding the further topics around VPC or subnetting or other deeper concepts. And if you have any questions or clarifications, please feel free to drop your questions in the comments. I will try to answer to each one of them. If you like this video, please do not forget to like and subscribe to support the channel and the work that um, and the information that I'm trying to bring back to you. So thank you for today. See you in next video.